Hi, in this video, I'm going to teach you how to perform hypothesis testing on one population proportion. As you will see in this example, the process will be the same to that of the testing on one population mean, and it will have only a slight difference when it comes to the formula that we are going to use in a particular step. Okay, so in learning how to perform hypothesis testing on one population proportion, I'll be showing you one example. So let us consider this scenario. A group of students would like to know the opinions of the students in their school regarding the possible extension of the enhanced community quarantine. Out of 150 randomly selected students, 122 of them believe that the quarantine will be extended after the scheduled date that it is supposed to end. Is there sufficient evidence that the proportion of students who believe that the quarantine will be extended is higher than 80% at 1% significance level? So it is clear from the example that the focus of this scenario is on testing a certain proportion, and that it has a sample of 150 students, and out of those 150, 122 believe that the quarantine will be extended after the scheduled date. So there is no mean that is being talked about in this problem, and this is all about proportion. So we will be performing a hypothesis testing on one population proportion. Now it's one population proportion because, as we can see, there's only a single group of sample that was considered, and that's 150. Now, why is it called on one population proportion? Because there is also another case in which you will consider two population proportions. Okay, but this is an example on one population proportion. So how do we proceed with the testing? We will be using the 5 steps version of the hypothesis testing. So step number 1, that is the writing of the null and alternative hypothesis. Now this is a good example of proportion or hypothesis testing on one proportion, because this is where we do not need to write first the null hypothesis. As we can see from the statement, it says that what we want to test is if there is sufficient evidence that the proportion of the students who believe that the quarantine will be extended is higher than 80%. Now we cannot make the p greater than 0.80 to be our null hypothesis. So do not fall into the trap of always writing first the null hypothesis. There will be cases, and in this example, that the alternative hypothesis is written. But what makes this statement our alternative hypothesis? Now, we don't have a status quo, so we don't exactly know if it's already said that it's greater than 0.80 or less than or at least 0.80 or at most 0.80. But our only statement here, where the question is it higher than 80%? So we have to use that other rule when writing the null and alternative hypothesis, in that the alternative, or rather the null hypothesis, will always contain the equal sign. Now the statement is saying it will be extended, the proportion is higher than 80%. When we say higher than 80%, it doesn't include 80%. So that's greater than 0.80. So we have to write that as our alternative hypothesis. So the proportion P, take note this is not a P hat, the proportion P, the population proportion P, must be greater than 0.80. And with that alternative hypothesis, we can easily write our null hypothesis, which is P is less than or equal to 0.80. Now, in other instances, we can even write our null hypothesis to be the proportion is equal to 0.80, and that's a valid null hypothesis, that it is equal to 0.80. In terms of the writing, there is either of these two will be accepted as our null hypothesis. Whether you say that it is less than or equal to 0.80 or it's the proportion is 0.80, you can use any of the two. Okay? But just take note that what our goal here now is that we need to find evidence to support the claim that the proportion is higher than 80%. And that's the only goal. Otherwise, either of these two is correct. It is less than 0.80 or it is equal to 0.80. But saying that greater than 0.80 can be valid or invalid depending on the evidence that we can have. Okay? So that's for step number 1. Then we go to step number 2. The step number 2 is about identifying our significance level, or if it is given already, then we can just get that value. Determine what is our test statistic as to whether it is a Z or a T, and how we should state our decision rule. So let's start with our significance level alpha. It was mentioned in the problem that the significance level to be used in this testing is 1%. So our alpha is 1%. For the type of test, you use the z-test if you can show the following. So the condition is that the np sub 0 must be greater than 5, or not or, and the nq sub 0 is also greater than 5. Now from the data that we have, so n is 150, so from our problem, so this is 150, and the p sub 0 is the hypothesized proportion, which is 0.80. So 150 times 0.80, and then compute for this number. 150 times 0.80 is 120, which is obviously bigger than 5. So condition number 1 is satisfied. For the second condition, nq sub 0 must be greater than 5, so we check that. So that means 150, and q sub 0 is the complement of p sub 0. So if this is 0.80, then the q sub 0 must be equal to 0.20 to make 100%. So times 0.20, when you compute for this number, the value is equal to 30. And 30 is bigger than 5, so the condition 2 is met. Therefore, the test that we have to apply is the z-test. For the decision rule is guided by the alternative hypothesis. So our alternative hypothesis says that we have p greater than 0.80, and this signals a one-tailed test, and the tail is determined by this inequality sign. It's greater than. A greater than sign would mean that the area of rejection will fall on the right side. Some people use the direction of the inequality to signal or to lead us to what region should we shade. Okay, so the area of rejection will be on the right side. And with that, since the area of rejection is the area alpha, and our alpha is equal to 0.01 because it's 1%, then there is no need for us to divide the alpha into 2, because dividing the alpha into 2 will be needed only for two-tailed tests, but this is just a one-tailed test. So the 0.01 will be that whole area that we see on the right. So this is 0.01. And later on, we will be noting this boundary, and that boundary is z of 0.01, which is a number that we will show later in the other step. So with that, once we compute for this z value, which will be given by p hat minus the p sub 0 over the square root of p sub 0 q sub 0 over n, if this number z will be higher than z of alpha. Now the z of alpha is 0.01. If it is higher, then that means the value will fall in the critical region, and that means in the area of rejection. If that will happen, then the corresponding conclusion must be, or the decision is to reject the null hypothesis. Otherwise, if the number will fall on the region outside the critical region, and that is any number lower than the z of 0.01, then the decision must be fail to reject HO. Now, once we know the alpha, once we know the test statistic to be used, and the decision rule, we will now proceed to step number 3, and that is the computation of the test statistic z. So again, the formula to use here is z is p hat minus p sub 0 over the square root of p sub 0 q sub 0 over n. The p hat, as we already know, is x over n, where x is 122 and the n is 150. If you will compute for this value, the value is 0.8133, so this is rounded off up to 4 decimal places. Now the p sub 0 is the hypothesized proportion. Now based on our null hypothesis, the null hypothesis says that it is less than 0.80, so the proportion 0.80 is our p sub 0. So here we have p sub 0 is 0.80, and if p sub 0 is 0.80, then the q sub 0 is 1 minus p sub 0, which is 1 minus 0.80 equals 0.20. So if we will supply this formula with the corresponding value, so we have p hat is 0.8133 minus p sub 0 0.80 divided by the quantity, the square root of p sub 0, which is 0.80, q sub 0 0.20 over the 150 sample size n. Use your calculator to find this number and you will find it to be 0.4072. And that's the computed value for the z. And after that, we immediately go to the fourth step. In the fourth step, we'll be comparing our z-test statistic, the computed z, which is 0.4072, to that of the critical value z of alpha. So again, in our diagram, we have a right-tailed diagram, and the area of rejection is located here. So the z of alpha, which is z of 0.01, is given by 2.33. And this value can easily be taken if we have a reference for the special z values. So the z of 0.01, so like in this list, is the value 2.33. So that boundary that we see in our area of rejection is this number 2.33. So to compare the z-test statistic value, the one that we have computed as 0.4072, we have to place this in our diagram. Now, since the boundary is at 2.33, we should see that the 0.472 is located at the left of that number, so somewhere here. So if the middle is 0, so the value 0.4072 is a number close to 0 and it is less than 2.33. Now, based on the idea, if this number will fall outside the area of rejection, then our decision is failed to reject HO, because again, in our step number 4, the z-test statistic fell outside the area of rejection, so we fail to reject HO. That means there is no sufficient evidence to support our H1, and that is the proportion of students who believe that the quarantine will be extended is higher than 80%, and this is at 1% significance level. Hence, we can say that less than 80% of the student population in their school believe that the quarantine will be extended. Now, we don't exactly know how many percent, but what we know right now is that it is less than 80%. Now, if somebody would like to find how many percent or to estimate, then that is a good example of an estimation of a proportion. Okay, but for this video, since our objective is to learn how to perform hypothesis testing on one population proportion, so we will end with this decision and conclusion. Okay, so that's how we perform hypothesis testing on one population proportion. So we are following the 5-step version so that you will know exactly what to do from the start of the testing up to the last step. So again, we start with the null and alternative hypothesis writing, and the writing of this hypothesis will depend on the statements given in the problem. Number 2, the significance level, the test statistic, and setting the decision rule. Number 3, the computation of the test statistic, which will depend on the formula for the test statistic, and this formula will vary depending on the uh, topic that you are studying. If it's a population mean, then you have to use the Z formula for the mean, but if it's a test on population proportion, then you have to use the Z for population proportion. And from there, you compare the test statistic value that you have computed with the critical value. Now here I emphasize, which is one good thing about this example, is that there is no need for you to divide the alpha into 2, because that is the only, or that will only happen if we have two-tailed tests. But there's only one tail in our diagram, so there's no need for you to divide the alpha. So the 0.01 will be the 0.01, and that value can be taken from a list of special z values. And from there, once you compare the test statistic and the critical value, you should be able to come up with the right decision. And in this case, we failed to reject. We cannot reject the null hypothesis that it is less than or equal to 80%. And again, we said we don't know exactly how many percent, but what we know is that it is less than or equal to 80%. Or just to state the it in relation to the claim, because the claim was it is greater than 0.80, then we say it is not greater than 80%. Okay, so that's how we perform hypothesis testing on one population proportion. That's it. Thank you.